thank you for coming to our Georgia Tech College of Sciences Frontiers in Science lecture series. My name is Matt Baker, and I am an Associate Dean in the College of Sciences. And we put together a year-long lecture series celebrating the 150th anniversary of the discovery formulation of the periodic table by Bloated. And we've had a number of talks focusing on different aspects of the periodic table of elements, from astronomy to the silicon and its properties that make it such an important element in society, to the mathematics of the periodic table. And today we will have a lecture on ocean chemistry and its relation to global warming. Next month we have our last lecture in this series, so November 12th at 6:30 p.m., not here but in the Sadath room, which most of you I think know where that is, in IBD. We'll have Margaret Kosal talking about the geopolitics of rare elements. Anyway, tonight we have a special guest from the School of Earth and Atmospheric Sciences, and in order to introduce our guest, but before I do that, sorry, we have one important piece of business, which is that afterwards there will be 10 lucky winners of a College of Sciences t-shirt. And you will have to stick around for the question and answer afterwards in order to find out whether you are or are not a winner of our contest. We do this after every lecture in the series. Okay, so now it's my pleasure to introduce Greg Huey, who is the chair of the School of Earth and Atmospheric Sciences, and he will introduce tonight's speaker.
Thank you, Matt, and thanks to everybody for coming out tonight on a cold, rainy Halloween. I think we have an excellent turnout, given the situation. My 11-year-old daughter is trick-or-treating, irregardless of my presence here, so everybody else was able to make plans as well. It's truly an honor for me to be able to introduce tonight's speaker, Taka Ito. Every time I get to introduce one of our faculty members, I'm chair of the School of Earth and Atmospheric Sciences, I kind of think, why are all the faculty better than me? They're such fabulous researchers, and Taka is no exception to this. He is famous in the oceanography community for being able to separate out very complicated problems to try to understand what's going on in the natural system. And just to give a little background on how important the ocean is, I think most of us understand that. However, its role in the climate system is probably not so well understood. For example, a good fraction of the CO2 that's emitted from anthropogenic and other activities ends up dissolving on the ocean. How that exactly happens, for example, in large swaths of the Southern Ocean where we don't have a tremendous amount of data, is not so obvious, and Taka is an expert on that in the Southern Ocean. A lot of the oxygen in the atmosphere is generated by the biology in the ocean, for example. However, the amount of oxygen in the ocean is going down, and Taka is an expert on trying to understand why that's happening. So please join me in welcoming Taka Ito to tonight's speaker. Thank you very much.
Thank you very much for the very nice introduction, and I'm truly honored to give this presentation as a part of the series of talks on the International Year of Periodic Table. So my name is Taka Ito, and I teach physical and chemical oceanography in the School of Earth and Atmospheric Sciences at Georgia Tech. So I'm very happy to talk about my favorite subject, the ocean chemistry, today. And here's just a brief outline of my talk. I'd like to start with a periodic table for oceanographers that help us understand what's happening to the chemistry of the ocean. So I want to transition to more of changes that we observe in ocean chemistry today in the second part. So let me just dive in. Excuse me. So in the late 1990s, Nozaki sensei is a chemical oceanographer from Japan, and he put together a periodic table of elements dissolved in the seawater. And what's interesting is this diagram is that he encapsulated the vertical profile of each element that's observed in the North Pacific Ocean for each element. So there are, as of 1990s, there are already more than 80 elements measured in the seawater. And each box here, I'm sorry, it's kind of hard to see, but it's a vertical profile. So x-axis is a concentration and y-axis is depth from surface to 5 kilometers, so the bottom of the ocean. And also he put together the different symbols, so it indicates the overall amount of concentration. And these data, I'll go into more detail in a few slides. But these measurements come from the research crews on the ship, and it's a lot of work to sample waters. This is the water sampler, and there's the winch that sends these samplers down through the water column, and often we analyze on board. So this is a picture from several years ago when I was on this cruise, and I was making a Winkler titration to measure oxygen. A lot of work went into making these data sets. And so Nozaki sensei found several patterns in the distribution of elements in the ocean. I boxed these high concentration elements here in the blue box. So I highlighted them. Those are the ones that are relatively high in concentration, higher than a millimole of these elements per liter of seawater. And these are main ingredients of sea salt. You can see alkali metal, alkaline earth, and some halogens like chloride ion and sodium, magnesium, potassium, calcium. These are main ingredients of salt. There are some intermediate concentration elements, not many, nitrogen, oxygen, silica, phosphorus. These are important macronutrients in the ocean. Those are in the order of 1 micromole per liter of seawater or higher. And the rest are called trace elements, very low concentrations, on the order of nanomole or picomole per liter. And those takes up the bulk of the periodic table. And he also identified there are several patterns of this vertical structure. Some elements are conservative. We call it conservative. The vertical profile is almost uniform vertically, so the concentration is about the same everywhere. And high concentration sea salts mostly following this pattern, and some trace elements are also conservative. This indicates that they don't react very quickly. And so over the long time, the ocean mixes, and it tends to homogenize the concentration. So we also call these non-reactive elements. And eventually, they will get buried into the sediment, and they originate from the breakdown of rocks on the land. It's called weathering, and the river runoff will transport the elements in. But they spend millions of years in the ocean, so the ocean circulation has time to just completely, almost completely homogenize them. And that's main ingredients of sea salt. He found another group of elements that behaves differently. Those are the ones that's high concentration near the surface, and as you go down with depth, the concentration decreases. And these are called scavenged profile. And there are several of these trace elements, such as aluminum, manganese, and several others that has this profile. And what this seems to indicate is that they have a common mechanism that form this distribution. So we think of these elements coming from the atmosphere, deposition of aerosol, that comes and deposit those dusts from the atmosphere, and that's the source. And it enters in the ocean, but these trace metals are reactive to the particles. So it sticks to the marine particles that are present in the ocean, and it sinks out. So the source is at the surface, and then it's absorbed into the particles in the subsurface. So it creates a pattern that's decreasing with depth. And then there are another type of elements that has opposite pattern that's low near the surface, and it increases with depth. And this is called nutrient-like profile. In fact, all of these macronutrients, nitrogen, phosphorus, silica, these elements are low near the surface, and then it goes up with depth. But so is many of the trace elements, and I still find it very interesting how the many trace elements are also behaving like nutrients. So the underlying mechanism that's shared with these elements, likely that we have active photosynthesis and production of organic matter in the surface ocean. And these living organisms will consume the nutrients because they use the nutrients from the water to build biomass. So the surface water is depleted in nutrients. And those organisms produce organic matter, making particles that sinks through the water column. And as it sinks, those particles decompose back into the inorganic form. So it releases these elements back to the water. So the biology is essentially taking up the nutrient from the surface and then sending it down and releasing back to the water. So it creates this vertical profile that enriched at depth and depleted at the surface. We call this a nutrient-like profile. So that's obviously what dictates the major nutrients like nitrogen and phosphorus. But it also affects many trace metal elements that I find very interesting. But back in 1990s, there were not many observations of these trace elements. This is a diagram I took from this paper by Tagliabue, 2016. This is a number of dissolved iron measurements as a function of time. So you can see back in 1990s, we have only a few hundred of iron measurement. That was enough to produce a vertical profile like this. Iron also has a profile like nutrient-like, but we have a lot more measurement in recent years. So what's been happening in the last 20 years or so is that making these profiles of trace metals three-dimensional. So we have more structure that we now observe. So this is a sort of state-of-the-art of measurement of iron in the ocean from the GeoTraces project that's been going on in the last decade or so. So what we see in this color shading is the concentration of dissolved iron in the seawater following the pathway of research cruises. So these curtains of color shading is following the research cruise, and then it's plotting the iron concentration as a function of depth. So we see sort of more of a three-dimensional structure. And so you can see that near the surface, the blue or purple color is showing very low concentrations. So near the surface, it's generally low, and it's enriched at depth. So we still see this profile, but we also have a lot of horizontal structure, such as these features, high iron coming off of the mid-ocean ridges, and these are thought to come from these black smokers. The hydrothermal vents are important source of dissolved iron. Now we document in these data. So this is something that we work on in our group to model this iron distribution in the ocean. We now think that the system is a lot more complex, that we have multiple sources, not just from the atmospheric dust deposition, but also iron may come from the seafloor sediments and also hydrothermal vents. And we know that it's an important nutrient, so it has signature of biological consumption at the surface, and it sinks with the particles, but also it's scavenged onto the particles as trace metal. And also it forms an iron ligand complex in the water. And this complexation is very important because these iron ligand complex are dissolved in the water, and that is not scavenged onto the particles. So it maintains this nutrient structure. So we are continuing to learn the mechanism behind these profiles for trace metals. And I want to switch a little bit to the human impacts, the coastal eutrophication. Here I'm talking about nitrogen sources coming from the land. Discharge of nutrients from the fertilizer and wastewater tends to increase the nutrient levels of rivers and estuaries. And this is a very important problem because higher level of nutrient causes algal blooms that produce toxins, and it produces a lot of organic matter. If it decays, it consumes oxygen and also produce local acidification. So it's an important coastal environmental problem. This is a map of the nitrogen loading for the estuaries along the US coast. So you can see Mississippi River gets a lot of nutrient from the fertilizer use in the upstream, and we also have a problem in the mid-Atlantic coast, more from the wastewaters from the population centers. But most of the estuaries have some degree of eutrophication, and it mainly reflects the nutrient loading, although each estuary is different. So this map shows sort of the overall eutrophic condition that mostly mirrors the nutrient loading. And I want to talk a little bit about oxygen. Oxygen is an interesting element. It doesn't look like any other elements in the sense that this looks more like a reverse of the nutrient profile. And yet this is very important for life. All marine life needs oxygen for metabolism, and surface water is relatively enriched because 20% of atmosphere is oxygen, and exchange of gases between the ocean and atmosphere tends to keep the surface water close to saturation with the atmosphere. And the saturation concentration of oxygen is strongly dependent on temperature. So here's temperature as x-axis, and saturation oxygen on the orange line. It's a decreasing function of temperature, so the warm water holds less gases. And the blue dots are individual measurements from the surface water, so it mostly follows this saturation relationship. In the subsurface, oxygen level goes down because of the decomposition of organic matter at depths. Where the surface, oxygen is produced by photosynthesis and it degasses into the atmosphere, while the organic matter that's left behind will sink into the interior ocean, and as it sinks, it decays back into the inorganic nutrients and carbon. At the same time, oxygen is consumed at depth. And so the biology is consuming the subsurface oxygen, and that loss of oxygen has to be replenished by the physical circulation that's transporting the relatively cold water from the high latitudes, physically transporting it. So in order to maintain the dynamic steady state, the loss of oxygen by the biological processes has to be balanced by the physical transfer of oxygen by the ocean circulation. So that kind of maintains this shape of the oxygen profile in the ocean. And this is something that we spend a lot of time studying. We authors think that the oxygen is changing in the ocean. Part of it is because of the fact that ocean is warming up, and the warm water through the thermodynamic relationship. The number is not very important, but warming of the ocean tends to lose oxygen over time. And the second factor is also important, that when the ocean is heated, it's heated by the surface, heated at the surface ocean. So it tends to increase the stratification of the ocean, that the surface water is warmer and less dense, and that surface water is even getting warmer, while the deep ocean remains relatively cold. So the density difference between the surface and at depth is increasing as the ocean is heated up. And we think that that's going to reduce the physical supply of oxygen into the interior ocean, because the surface mixing, then convection at the surface has to get weaker as you increase the density contrast between the surface and at depth. So the second effect is relatively less known. So we have been asking how much oxygen change has happened in this instrument record of the ocean. So we've looked at the World Ocean Database. This is an international collaborative project where data centers and individual laboratories submit observational data to this data set. And as of 2013, oxygen profiles, there were about a little bit short of 1 million oxygen profiles. So that makes oxygen the most frequently measured chemical element in the ocean, following temperature and salinity, of course. So we have looked at this data set and developed a three-dimensionally gridded and time-resolved data set of oxygen, and we calculated the temporal change of upper ocean oxygen inventory as a function of time. So that's the upper left panel. This purplish line that goes doing this ups and down is the oxygen inventory in the upper 1,000 meters, globally integrated. So there was a period of a little bit of increase before 1980s, and then after 80s we have this strong decrease. So that's the pattern we find, and the horizontal structure. So if we take a linear trend at every grid point and make a map, we have a pattern like this. This pattern is not complete in the sense that there's a lot of missing data, especially in the southern hemisphere oceans away from the population centers. But nonetheless, we see more red than blue. That means the red regions are the regions that oxygen is decreasing. So we see North Pacific and some part of the tropical oceans are losing oxygen, also in the southern hemisphere high latitudes. Again, the number is not so important, but overall, in the last 60 years or so, approximately the ocean seemed to have lost about 2% of its oxygen content. So that's a result from this study. We can also look at this in relation to the rate that ocean is warming up. So this is heat content of the ocean based on ORAS-4. This is a data set that developed by the ECMWF, European Center for Medium-Range Weather Forecasting. So we use their data set to calculate the heat content change. So this is the general increase of heat content increase over the same time period. So we combine that together and make this diagram where the x-axis is the heat content and the y-axis is the oxygen content, and trying to look at the relationship. As the ocean warms up, we move to the right, oxygen goes down. So we have this downward sloping line to the right here. And each dots are coming from the annually averaged combination of oxygen and heat content. So approximately we have this slope that is about 32 micromole per Kelvin. That's the observed oxygen to temperature ratio. And what we would expect from the thermodynamic solubility of the oxygen is about this slope, this blue line here. So it's much shallower slope than is observed. And that indicates that about a quarter of the oxygen loss comes from the warming of the ocean. And the rest, so that is the 3/4 coming from the non-solubility effect. And we think that to some extent that has to be explained by the circulation changes or the changes in the biological processes. So understanding this, how this works is still an open question. And I would also like to talk a little bit about carbon, since this is also such an important element. Carbon has a nearly constant profile, but also it is nutrient-like because it's an important building block of living organisms. So what's interesting about carbon is that if you look at how much carbon dioxide exists in the atmosphere, it's about 800 petagrams of carbon. Petagram is the 10 to the 15th grams of carbon. In the ocean, we have about 40,000, so more than 90% of carbon in the ocean atmosphere system is in the ocean, and this remarkable size of the ocean reservoir of carbon is due to the charge associated with the charge balance of the ocean, where we have a lot of these positively charged ions in the ocean, and that's coming from this weathering of land, and over the millions of years, ocean accumulated this sea salt. And if you look at the charge, electrical charge of this sea salt, it's slightly biased towards the positive, and that positive charge has to be balanced by these carbonate species. So, and we want to have a net neutral. If you think of the electron balance of the ocean, we have to have a net neutral, so we have to have a lot of these carbonate species to balance the charges from the positive charges from the salt. And the biological processes also utilize the carbon sending into deep ocean, so this kind of explains the vertically enriched profile. And that's further enriching the deep ocean carbon reservoir. So what's happening is that we are adding more and more CO2 into the atmosphere. We are adding the CO2 into the atmosphere, and that goes into the ocean. The main reaction is that the CO2 goes into the ocean, and it combines with carbonate ion and water molecule to form bicarbonate. And the bicarbonate, the HCO3 minus, is the major carbon species in the ocean. About 90% of carbon in the ocean is in the bicarbonate, and 10% is the carbonate pool. But in any case, the ratio between these two guys is actually what's determining the pH of the seawater. So as we increase more and more CO2, this reaction shifts to the right, and we are increasing the bicarbonate at the expense of consuming carbonate ion. So over time, the hydrogen ion concentration, the acidity of the water is going up. So this is the, okay, next slide here. So this is the turning sour part that in the last decade or so, on average, the international CO2 emission is on the order of 9.4 plus or minus a half petagrams of carbon per year. Out of this, about less than half remains in the atmosphere that contributes to the rise of the atmospheric CO2. About half is disappearing from the atmosphere. About a quarter goes into the ocean, and another quarter goes into the land. So ocean is doing a great service in terms of slowing down the buildup of CO2 in the atmosphere. But because of the reasons we saw in the previous slide, the pH of the seawater is decreasing, and the acidity of the water is going up. So far, since the Industrial Revolution, we have seen about a 30% increase in the hydrogen ion concentration, and that's a substantial increase. I'm coming close to the end, and I wanted to talk a little bit about the ecological impacts. The rate of change of this ocean pH is 10 to 100 times faster than any period in the last 50 million years of the Earth's history. So this is literally unprecedented rate of change of the Earth's environment, and the pH is important for the stability of calcium carbonate. That is an important a shell or skeletal material for living organisms, and the shellfish, especially the early young stages, are known to be vulnerable for the acidification. So this is the acidification of the ocean is becoming an important concern for fishery and ecosystem. But I want to end with a little positive outlook on this story. There was a really interesting story from the Pacific Northwest shellfish industry. It's a $270 million industry supporting more than 3,000 families in the rural parts of Northern California, Oregon, and Washington coast. And what happens in 2007 was that there was a near collapse of oyster hatcheries that produces oyster seeds for the oyster growers in the region. This happened in the Oregon coast. And the hatchery operators were looking for reasons. First, they doubted that the harmful algal blooms and the production of toxins are doubted cause of the mass mortality. The mortality was more than 80%. But in a few years, they started to collaborate with scientists from the Oregon State University and the NOAA PMEL. They determined that the actual cause of the mortality was the higher acidity of the water. And within the few years, they actually developed the adaptation strategies to mitigate the effect of this acidification. This is a microscopic image of the oyster larvae, the oyster seeds. 1 day, 2 days, 4 days after the fertilization of the egg. And at the early stage, as they develop their shells, this is under the normal condition, and this is high CO2, so they demonstrated that the CO2 has a major effect on the development of these oyster seeds. But the amazing aspect of this story was that they reacted so quickly and developed a scientifically based solution to this problem. This diagram is showing that what's really important in this problem was actually the saturation state of aragonite. That's a certain form of calcium carbonate mineral. And they determined that that's related to the production rate of the oyster seeds, which is the y-axis, and found the threshold 1.7 in this unit is going to be the threshold for commercially viable operation of the hatchery. So they developed the real-time monitoring of the water quality, and they only use the water, open the water intake under the water condition that is good. And also they developed the pH buffering system to add sodium carbonate into the tank when the pH was too low. So I think this is a very positive story that science and the fishery community work together to develop the solution. So this is my last slide. I hope that I was able to convey some of the understanding behind these current ongoing changes of the changes in the ocean chemistry, and the importance of taking actions, acknowledge the problem, and also I think developing the resilience, localized and science-based solution opens up really new sets of scientific and engineering questions and opportunities. So with that, I'd like to finish my presentation. Thank you very much for your attention.
So thank you very much for that talk. We have time for questions. Are there any questions in the audience?
What would be the implications if the Atlantic overturning current collapsed as far as carbon, oxygen, what remains at the surface, and what still would happen at depth?
I think, so the question was, what would be the consequence of collapsing, or if the Atlantic meridian overturning circulation were to collapse, what would be the consequence on nutrients, oxygen, ecosystem? I think that's very important questions, and actually I think we have something to say. We are working on these problems because there is a model projections that as the warming continues, the overturning might weaken. We think it's an important transport pathway of nutrients to the North Atlantic Ocean. And there is a term called nutrient stream. And actually, Dean Rose is one of the pioneers who developed this concept. So we think that if it weakens, it will reduce the supply of nutrients to the North Atlantic Ocean. So it will likely reduce the potentially reduce the biological productivity by a significant amount. What that does to oxygen is interesting. Because of the weakened biological productivity, there will be a less production of organic matter. So, and the sinking organic matter is a major sink of oxygen. So you might end up having a less oxygen loss because of having less organic matter production. So that's a hypothesis at the moment. But I think there would be a far-reaching influence.
I've heard it suggested that one solution might be to put small iron particles to kind of seed the ocean with small iron particles. Is there anything to?
Right. So the question of fertilizing the ocean potentially as a way to mitigate problem with CO2 because increase the ocean productivity that will suck up the CO2 from the atmosphere. So I think that idea has been around for quite some time, and also people have conducted in situ and also modeling experiments. So my understanding is that it does increase biological productivity locally. However, the effect on the carbon uptake part is not so clear. And the reason is being that I think one reason is called the downstream effect, that locally it can produce the biological carbon uptake, but it will consume other nutrients in that region, and that might end up productivity being decreased in the downstream region. So as a whole system, it may not be as effective. I think there are several ideas that counters the idea of fertilization. But I think there may be still people thinking about that possibility. Yeah.
Do you mind
Thank you.
if I just add a quick thing about that?
Sure.
Just the interesting thing about iron fertilization, the idea was to bring the CO2 out of the atmosphere, right, a drawdown, because we don't want any more CO2 in the ocean. So a lot of the idea about the iron fertilization really, I think in some ways predated our understanding of how much CO2 was in the ocean and the impacts of that in terms of increasing acidification. So it's pretty controversial about what are the downstream consequences then, or the unintended consequences of adding, that increasing the CO2 drawdown. So we have too much of it, but keeping in the atmosphere isn't good, but we don't necessarily want it in the ocean as well. So I just want to add that little bit of
Thank you.
context.
So in a similar vein, I'm asking about phytoplankton and their ability to fix carbon dioxide and make calcium carbonate that drops to the sediment and coats the ocean floor as a means of massive carbon sequestration. Has there been any concerted effort in providing, cultivating climate for these phytoplankton that you know of?
So the question about calcium carbonate production and sending it down to the seafloor sediment is actually a very interesting problem, but actually it would end up increasing the atmospheric CO2 because of it is being calcium carbonate. It is denser, so it's easier to sink for sure. But what happens is that when you form calcium carbonate, you are taking away calcium ion from the water, combine it with carbonate to make calcium carbonate, and then they are both exported to the seafloor. And that has different effect than making organic carbon and sending it to the deep ocean. And the difference is that the calcium carbonate has calcium ion, and calcium ion is positively charged. So you take away that calcium 2+ from the surface ocean, and it end up making the surface water more acidic. Even though you're removing carbon, you are removing more calcium ion salt from the surface ocean. So your so-called alkalinity level is decreasing more than you decrease carbon. So it is known to actually increase the atmospheric CO2. So the parts that are important for drawing down atmospheric CO2 is the organic part. That's the part that we want to be stronger if you're thinking of the lowering CO2 in the atmosphere.
I hate it when there's no free lunch.
We found that out a long time ago in the economics and business industry. If you're looking at your data set seems to be extremely expensive to acquire and very limited in a lot of ways. You know, it's basically a winch going down, and I assume there's actual samples that you bring up at that point that you have to analyze. So there's really two parts to this question. One is, have people looked at, instead of using a winch, using autonomous undersea vehicles, drones, to do sampling in a widespread way where the boat wouldn't necessarily have to sit there, but could put a number of these out and then come around and pick them up? The second part of it is, if you look at the atmospheric gas sampling, to a large degree because of wanting to be able to monitor a lot of emissions from oil and gas drilling operations, there's been a real explosion of different new sensors to automatically be able to measure these things. So if you didn't have to pull a sample up, but you could do a sensor, is there anything like that that's emerging in technologies that would allow you to get a much broader data set than what you're limited to now?
Yes, I definitely agree with your comments that has to be the future. And for oxygen, nitrate, pH, and a few other things, we do have a solution that is autonomous, and so those robotic floats that can be released and be operational for years and making hundreds of profiles for life cycle are now available and deployed in certain regions of the ocean, not globally yet, but I am really hoping that we have the global coverage of those autonomous sensors that would increase the amount of data by orders of magnitude. Yes, so I definitely agree.
Let's have a couple more questions.
So you compared the pH pH change in the last 60 years to much larger orders of magnitude before that, but since we only have data that's collected pretty recently, how do you predict that?
Well, so prediction is difficult. However, and we can use, one way is to use models. We have to build in assumptions, but there are model-based projections really. Under different scenarios, we can project how much CO2 is going to be there in the atmosphere. Then we can calculate what would be the projected pH level going to be. pH is probably easier to predict because it's strongly related to the CO2 levels. So we can do based on the mechanistic model-based projection, and that's probably the best tools we have.
This is a question that relates to possibly politically helping the state of Georgia. You may have heard of the water wars, and Georgia's locked into almost decades-long fight with Florida, over particularly the loss of the shellfish in the Apalachicola estuary, which is basically the end of the Chattahoochee River. And Florida blames it on not getting enough fresh water because Atlanta sucks it all up. And you're mentioning that the pH change back in 2007 in the Northwest. I'm wondering if there's any information that you're aware of, or which we ought to put together to help Georgia see that actually it's the pH change in the Apalachicola Bay that's causing their diminishment of that industry.
Thank you very much for the question. I am actually not very familiar with that particular estuary. So, but it's the question is Georgia is not releasing enough fresh water.
That's the implication.
Right.
Of the application from Florida. And I'm wondering if there's another explanation.
I am getting interested in this program, but at the moment I don't really have much information that I can offer, I'm afraid.
I think an excellent hypothesis has just been formed that someone will need to do experiments with. So we have a little gift for our speaker for giving this excellent talk here today. So Taka, thank you very much.
Thank you very much.